Hey guys, it's Active Synergist. So today we have the ultimate proof of my Recastian standard distribution function, and this is Recastian dynamics or Ivankovian Recastian dynamics 101. It's the first lecture, and I'm going to lay out a problem in a world's greatest mathematicians puzzle book that I solved, and I'm going to lay out the derivation of this new distribution function that I call CG5. So CG5 will be derived before you, and here's the problem laid out. We have a square, and by a grid of squares inside the square that basically transformed into a rectangle of this transform length of the long side, this transform length of the small side, and if you break this up into a half and slice this however you wish, you can rearrange the pieces so that you have a rectangle. So this piece goes here, this piece goes there, this long piece goes here, and that one is the last one there, so you can solve the jigsaw yourself. And so we have that premise here, and also the parameter premise that area transforms result in two different area discrepancies in terms of what the result is based on these parameters. So in n equals 8, we get n squared plus 1, and n equals 11, we get n squared minus 1. So why is that the discrepancy between these parameters? And so over the areas for the trapezoids. So we have a transform that I'm using called the Recastian transform, or the Ivankovian dynamic transform. And so this transform is a potential energy formula, and I've used it as such. I've solved maybe like 35 problems or so, and counting. Them are problems I've solved with this equation. But I don't necessarily use the transform all that often. I used it to derive this Recastian distribution function, and I use the distribution function regularly. It's a lot of fun. Here's this derivation point here where we can take this transform and just substitute these values of A and values of S of n, and then do these operations separately. It's not necessarily a partial, it's just a formula. We need to solve these things separately and then substitute them in and then do the integral. So that's all it is basically. And how to get this S parameter is the main problem. But for A equals n squared in the original square. As you know, all squares have the same side length, so n squared is the area. And so I should have wrote area here, just to write something because I want to keep my hands busy. So I'm using a zeta transform, which I came up with, that runs in tandem with this Recastian operator. I use d sub n, but it's actually a different thing because it has a superscript that is actually a part of this transform. So the zeta operator basically makes this into n ds to the new cast 1 times 1 for each of these 1 by 1 squares of f of n. So f of n is basically now placed right here, where we take the natural logarithm of an integral and we have it all in the exponent of the natural exponent. So the n is moved out front, despite that there's operations on things going on with this part right here. So we're just isolating this and using n separately later. So what happens here is you basically substitute a in there. A is n squared, so it becomes 2n, and the parameter is 4n, so everything cancels to 1/2, and you take dn, and it becomes n over 2 to the n is the value for s of n. this follows naturally as this operator works that way. So now you can substitute S of n in here, and just like I said before, we're just trying to solve this separately so we can now get this value of the Recastian distribution. And if you do that after you plug these things in, you get this value right here, or rather the formula that I've been using nonstop, but it's only partially the formula because the next step is to use a quotient where you take an area for n squared on top and an area for n squared plus 1, just one variant of this parameter difference, one parameter input output thing. And so basically we get all the parameters after we do this. All of them work properly. And excuse me if this is supposed to be a 13. I don't necessarily remember the exact. I don't know if I have that problem solution on hand, so I'd have to look it up in the photo in my phone. When I took the photo, I solved it, and then I just kind of had to do other things for a while. So generally, you get this function right here placed in these integrals, but the bounds for the integral are different. 0 to n squared plus 1 on bottom, 0 to n squared on top integral bounds. And so after you get this, the problem takes on another Recastian zeta function, basically just solving for the separate sides of this transform function. So now that we've solved for this function, basically we have that a side for this square, and I'll just call it f of n equals n. So I'm going to take the zeta of ds of n, and I'm going to go n. Is that how I did it last time? Excuse me if this is not exactly perfect right now. Oh, it's n and s. So of the square. And so the function basically it becomes ds of this function of n, and it's again 1 by 1, which means there's basically two results to this when using it just as a regular transform, not as a this is actually not the right. This is a psi function. So my bad, not zeta. It's actually xi, which looks like this. And I like to draw a little circle underneath, or in like an attached circle like that, yeah, with like an orb. This is a fun artistic thing. So basically, next we substitute n here, but we use it as a function, so not necessarily. And what happens is it has a natural formula that basically goes n t. It's basically two things result based on this 1 by 1. T of this function of the large side plus 1. It's like that. That's the first one. That's the large side of things. And the second parameter is there's a bit of a spaciness in my memory right now about how to exactly go about using the new cast here, because I haven't done it in a couple of years. or maybe a year and a half. And so had a lot of hospitalizations and getting back on my feet over and over again. And that's just a joke. Take it for what it is. Here basically we see that it could be that you think that this n is always distributed out front based on how the cast works. It distributes it once, which normally is how it works when you distribute something. You have to distribute it once to the entire thing. The second parameter actually distributes this directly to the short side and just adds 1 to it. So what I was thinking is I formalized, and it kind of was working when I did this, that I distribute to the entire thing and have 1 over n as what this value should be. And it was working when I did a couple problems with it when I worked it out this way, but generally I don't yet know much about how to do it that way. So I'm just avoiding saying that, and that's why I have a bit of a cloudy spacey memory right now about that. But in general, after you get this parameter solution going, you can solve for the area just by multiplying these things together, and this transforms of f of L is just using this Recastian distribution right here, right there, and plugging in parameters, just one parameter, just this n parameter. Generally, that's the entire thing. So now I just find the area by multiplying these two things. So I'm going to avoid doing that. I'm going to say n plus 1. And now I'll find some space. I'll write it right here. So the area equals multiplied to this n basically just like that, except one more thing happens. There's always a catch with these Recastian distributions, is that this sigma takes, or not sigma, psi takes the ceiling of both of these things before you can use them. So that is basically the result that gets you the area of the transformed area of that entire thing. And that's what I named it right here. So if you have questions, please comment, and don't forget to like and subscribe. But you can basically just plug these things into your calculator. The Recastian distribution is used right here. This is the Recastian distribution with the parameters so n 2 to the n ln of n and ln of 2 minus n, or minus 2 rather. And I'll write it out one more time because it's easy to write. And so the bounds are different here, and that is substituted in right here. But this is basically right here is, in fact, notation's kind of off kilter. This is just the Recastian. This is CG5 with its 4 parameters. So this is CG5. I'll just draw CG5 like that this time. And multiplying, using the ceiling function, multiplying these things together, substituting n of these values, and you get the correct parameter outputs every time for basically all values. And thus you can even verify this, but there is a bit of a variance to things that still need to work out. So there's a bit of an error ratio somewhere there. So you can basically try substituting 0.7%, or excuse me, 7.7 in for both of these ceiling functions, and still for the 2 parameters in the book, and again, I don't know if it's 13 or 11, basically you can get the same results, but then for other parameters, it's a bit different. Not all of them, but some of them are different. And so it's interesting. It works for these 2 parameters, so I consider it good. And I also consider the Recastian distribution function a major success based on what I've done with it. So with that, I leave you with a word of advice. If you are doing mathematics seriously, be as creative as possible. Never give up on your creativity. Follow all the logic where it takes you, and have a lot of fun. I have fun with this all the time. Thanks. Bye.